And then as a final sort of step here, you can actually rewrite this as 1 over sine theta times 1 over cosine theta. And then 1 over sine theta is a reciprocal identity. That's cosecant theta. 1 over cosine is secant theta. And that is probably your final answer. So quite a bit there. Like there's a lot to just doing this one problem. Is that okay?
Yeah, so you converted the tangent into sine theta over cosine theta.
That's right. That's right. Like one of the general strategies is to convert everything to sine and cosine. And 1 over tangent, it's awkward to put fractions in the bottom. So that's why I converted it first to cotangent and then to cosine and sine.
Okay, so then after that, you find the common denominator by multiplying the left side by sine and the right side by cosine.
Exactly.
You get that, and then you use the Pythagorean theorem to make the top one. And then so the answer would just be the bottom.
Well,
oh wait, oh, you multiplied them. Okay.
Yeah, I mean the bottom is the common denominator, sine theta, cosine theta, sine theta, cosine theta. That's your bottom. And then the top reduces because of this Pythagorean identity.
Okay, I get it now.
All right. And then but there is a kind of a legitimate question here, which is like, well, when do you stop? How do you know when you're done? And that's a hard question to answer. You keep going until you've done everything that is available to do. And only maybe seeing these, a few times would like 1 over sine theta is cosecant theta, 1 over cosine theta is secant theta. Things like that.
Okay. Yeah, what I noticed about this unit is it just has a lot of you need to know that like tangent equals sine, cosine, for example. You just need to like convert stuff.
Right. So like some students say, oh, it's just all in the formula sheet. I got it. It is essentially page 2 of that reference sheet I sent in the top left. That's the that's the basis for a lot of this. Let me snip that in here. At least to start. You actually end up needing all of it. All right. So when we look at number 5 here, are you drawn? Does anything stand out to you when you're looking at it?
Well, I mean, it's already simplified with the top. Just the bottom is
kind of, but what is 1 over cosecant is a reciprocal. Which reciprocal is that?
It's sine.
It's sine. So this becomes sine squared theta on the left. How about on the right?
That becomes cosine squared.
Yeah. Now, if you go off and you try to make a common denominator here, but you miss this, you go down the wrong path. You take, if you go from A to B, there's a straight line, or you go, around. Like you want to take the shortest path. So now, how about sine squared plus cosine squared? Does that stand out to you as anything?
That'd be equal to 1 because it's the Pythag theorem or Pythag identity.
Pythagorean identities, yeah. And so when you see squareds, you are generally drawn to Pythagorean identities, but because of the reciprocal here, you'd want to probably handle that first. And see, just doing more of these helps to figure that out. I don't know if you're the type that where you're okay to like go off in the wrong direction for a while, knowing that you learned something, or if that really super frustrates you to the point you don't want to do it. These are kind of in that category of you may not always go the right direction to start. So this is it. I mean, this one's done. Any questions on that?
No, it's pretty straightforward.
Great. All right. Let's look at number 9. All right, so number 9, 1 plus sine t to the power of 2 plus cosine squared t. So if this were, and sometimes you just draw an analogy to like, if this was 1 plus x squared plus x squared, what would you do first to simplify it?
You would well, it'd become 1 squared plus x squared.
And don't forget the middle term. You want to FOIL it.
Oh yeah.
Yeah. So yes, you do the same here. You FOIL this. Okay, so would you FOIL that on the left for me and let me know what you come up with?
So you want me to multiply them?
Yes, yes. 1 times 1, 1 times sine, sine times 1, sine times sine.
Oh, okay. So wouldn't it be 1 plus 2 sine t plus sine t squared?
Yes. Or sine squared t. So that the squared goes, you can see that with the cosine, it goes before the variable.
Oh, okay.
Okay. Now again, your eyes should sort of be drawn to this. Whenever you see a sine squared plus a cosine squared, you should think to yourself, okay, I'm going to use one of the Pythagorean identities or the Pythagorean identity for that. So this part becomes just 1. Sine squared t plus cosine squared t becomes 1. And then you're left with combining like terms. You can combine the 1 and the 1. And this feels pretty good. This feels like it's probably done.
Okay, got that.
All right, so any questions on that? Feel like you kind of maybe have it down?
Yeah, I do.
All right. So the next grouping of problems here, they do tell you to factor. So I think these are more clear with like what to do. They're just different types of factoring. So it's a good place to remind yourself of what they are. We should do some, but maybe not all. So this is sine squared, and then that's a Greek letter. I think it's I don't even want to say I know what that is, but we'll just call it y for now. So this one is an a squared minus b squared. This one's a difference of squares. So if you recall, a squared minus b squared becomes a minus b times a plus b. And so your goal is to figure out, well, what is it? It's what squared minus what squared gets you back to the previous line. So in this problem, it's the sine y, and it's 1. Because when you square sine y, it becomes sine squared. When you square 1, it becomes 1. And that's your A and your B. You know, that's A, that's B. What's in parentheses. So if that's clear, this becomes sine y minus 1, sine y plus 1.
Can you simplify that further? Or is that it?
This is it. So if you were to FOIL this, you would end up going back to what you started with.
Oh. Okay, got that.
Got it. Okay. So 15 is like it. We should look at it, maybe do it, maybe not, but sometimes they're sort of disguised. This one is a disguised difference of squares. So like, and so like, again, what I'm looking at is it's something squared minus something squared. And A this time is everything under parentheses, and B is everything under parentheses. All right, so this becomes sine x plus 1, that's the A, minus the B, and then you got to do in parentheses, so sine x minus 1, that's the first one, times the same thing, sine x plus 1, plus, you don't need the parentheses with plus, sine x minus 1, like this. So on the left, we do want to distribute that negative sine x plus 1 minus sine x plus 1. On the right, we can combine like terms. So there's 2 sine x's, and the plus 1 minus 1 cancel. And then on the left, you can see the sine x's actually cancel, and you've got plus 1, so it becomes 2 sine x. So that's 4 sine x, like that.
How come the sine x plus 1's cancel to become 2?
Say that one more time, on the right or the left. Sorry, I didn't.
On the left side.
So the negative has to distribute to both. And then that's what causes it, because everything here is your A and everything here is your B. But whenever you're subtracting, you have to subtract the whole quantity, not just the first one. So they're both negative, or this becomes negative, this one becomes positive, one positive, one negative. And just the 2's are left. 1 plus 1 to get 2.
Oh, okay. All right, got that.
Like, there's a lot here. So I mean, I'm probably not great opportunity for you to work on problems, but if I were to give you something like cosine squared x minus 1, you should now be able to factor that into cosine x minus 1, cosine x plus 1, and that's the difference of squares. So that you might see. So 17 and 19 go into a different type of problem. So we'll look at that next. So there's always like an analogous problem from something you've seen before. So this is like 2x squared plus 3x plus 1. And the instructions say to factor, so you're supposed to find two numbers. Well, this one's a grouping problem, but you can also use kind of a guess and check approach and find out that this works on the right when you factor. And so the same is expected here. It's expected that you can on the left factor it. Now, if you want to use the x on the right here to like work it out and then go back and say, okay, it's really 2 sine x plus 1 sine x plus 1 because x is really the sine x, you can do that as well. Is that okay? Or I mean, hopefully, have you seen that before?
No, I haven't actually.
Okay. Okay, so let me maybe start over again so you can see that do a little differently here. So in math, they use what are called U substitutions all over the place. And you see this the higher levels of math. So if you let U equal sine x, and if you square both sides, U squared is sine squared x. So you go back to your original problem, and wherever you see a sine squared x, you put in a U squared. Wherever you see a sine x, you put in a U. And you transform this into something that you're supposed to say, oh, I recognize how to do that. So this you're supposed to be able to factor. Now the traditional way of doing this is it's a little bit over the top here, but you take the 2 and the 1. So 2 times 1, which is 2. And you take the factors of 2, which are 1 and 2, and then you use this grouping technique. So this 3u becomes 2u plus 1u plus 1, like that. And then you're supposed to be able to factor the first 2 with a GCF.
Yeah, makes more sense.
Okay, and then you factor a 2u out of both. Okay, which leaves you with u plus 1, and then u plus 1. And then you have to figure out what goes in the middle here, such that when you multiply it in, you get back to the previous line. So you put some number in here so that when you multiply in, you get back to this one, previous line. But you usually just look at the constant. So like, oh, if I multiply by 1, 1 times u is 1u, 1 times 1 is 1. Okay. And then you factor out the u plus 1, 2u plus 1.
Okay, got that.
Okay, so when you do all that, you now have to remember that, hey, we're not doing this in terms of u is really sine x. And so you back what you call back substitute, or put the original substitution back in, so it becomes sine x plus 1 over 2 sine x plus 1, like that.
Yeah, I got that.
Great. So 18 is really, or 19 is really similar. I mean, you've got the evens and the odds there, but we should look at 19 together, because it appears that this could be some factoring here that maybe you're not super familiar with. So let's look at this here. So this time your u is always the kind of the middle thing. It's in this case the secant x, and then you typically square it, so it's secant squared x, like that. So your problem, original problem, becomes 4u squared. You want to do it in terms of u, plus 3u minus 1. Is that okay for up to the step?
Yeah.
Now the factoring here, like if you were to go down your list of factorings, which I don't have off to the side, you'd be like, oh, it's not this one, it's not this one, it's not this one. If there's a one in front, you would do it a certain way, but because it's not a one, you do have to take that first and that last number, 4 times -1, and you get -4. And then what you're looking for now is two numbers that multiply to -4 but add up to +3. This is so I guess sometimes they show it as like a diamond now. Maybe you saw that in the classroom. I'm not sure. But oops. But then you have to arrange the numbers in such a way where you see all the possibilities, and then you ask yourself, do any add up to +3?
Yeah. -1 and 4 do.
Yeah. So you have a choice here. So it's either -1u plus 4u, or you can switch the order 4u minus 1u. They both work, but I think most students tend to prefer the one that looks nicer with the first term here. So bring that down, 4u squared minus 1. So now you're finding the GCF of those two. Can you tell me what that would be?
Wouldn't it be 4u?
It is 4u. Yeah. Inside parentheses is u plus 1. You immediately write that over here to the right. And what you really hope for is that you can find a number such that when you multiply it in, you get the previous line. So in this case, that would be -1. -1 times u is -u, -1 times 1 is -1. And then you got to factor again. You know, it's like double factoring, because this u plus 1 is in both terms. So it becomes u plus 1, 4u minus 1, like that. The like the thing in front comes here and this number comes here. The order doesn't matter. Like if you have 4u minus 1 first and then u plus 1, that's okay too. But again, like you have to remember that, oh, I'm actually doing this for secant x, not just u. I have to back substitute. So it becomes secant x plus 1, and then 4 secant x minus 1.
Yeah, that makes a lot more sense, because my teacher just did it without substitution.
Right, and it's a lot to take in first time you
Yeah,
see it.
it becomes a mess.
Yes. So this is something you'll do a lot in math, and be aware. It's kind of the same approach, just always make a substitution. Now, 21 and 23. We're not going to do these unless we have time at the end. You should ask your instructor about this one. This is difference of cubes. And then there's also sum of cubes. You should ask if that's going to be required. And then 21 is a higher order substitution. But we'll come back to those if we've got time. But I want to make sure we get to these identities here to simplify. So I'm going to move on to 25, if that's okay.
Yeah, that's good.
All right, so your very first strategy when you're simplifying these things is to always turn everything into sine or cosine if you can. What is tangent in terms of sine and cosine?
That'd be sine theta over cosine theta.
Good. And then the one on the right is already in terms of sine and cosine. And then you're really looking for cancellations or things that reduce along the way. Does anything stand out to you here?
The cosines.
Yeah, they cancel. So you can
Yeah.
cross them out. I'm trying to get to where I can do that. Cross out, cross out. And what are you left with? Just the sine theta. So that's where you kind of start. You always look for like, what can I change everything into? Sine, cosine, things like that. So let's look at 27. No, 29. Huh. Okay, we'll look at 29 next. Okay, so if you apply the same approach to this problem, if you're like, okay, tangent is really sine beta over cosine beta, and then it's all over cosine beta. So this one didn't really get better because the sine doesn't cancel with that. Would you agree?
No, it doesn't.
Yeah, it doesn't cancel. So sometimes you take a step, you're like, well, maybe that wasn't the right way to go. If you go back to the original, you might notice that sine beta, cosine beta are here. What is sine over cosine?
Tangent.
Yes. So it's really tangent beta. And then it's just like x times x is x squared. Tangent times tangent is tangent squared beta, like that. All right, so let's look at 33. There's probably some good ones in between, like between 25 and 29 and 29 and 33 to look at. You're always welcome to send over as much as you want for us to work on, look at. The problem like this, again, like probably strategy number one is to convert everything to sine and cosine. It's usually a good idea. The squareds kind of tell you might use a Pythagorean identity, not sure yet. But this cosecant is really standing out to me. It's like, well, what is cosecant in terms of a sine or a cosine? Can you tell me that?
So wouldn't the sine be 1 over cosecant?
It is, but you want to convert everything into sine and cosine, and sine is already there, but cosecant is not.
Oh, then cosecant is 1 over sine.
Yeah. Now, does anything stand out to you once it's in this once it's like this?
The sines can cancel each other out.
So what is remaining? What does this whole grouping become?
1.
Plus 1. Yeah. Now, sine squared over cosine squared, they're already in terms of sine and cosine. Does anything there stand out to you? Sine over cosine.
Tangent.
Tangent, yeah. So it becomes
But it'd be
tangent.
tangent squared, right?
Exactly. Yep.
Yeah.
And whatever you see a squared, and specifically when you see a squared plus 1, you should be drawn to the Pythagorean identities. Now the order doesn't matter. Like in this middle one here, it doesn't matter that it's tangent squared plus 1. If it was 1 plus tangent squared or tangent squared plus 1, they are equivalent. So what does all of this become?
Secant squared over, or secant squared beta.
Or x, yeah, in this case.
Yeah.
Yeah, and that's a small thing, but some teachers are really sticklers for that. Like they want you to use the same letter throughout. I don't really care, but you want to do what they think, what they want. And if you write theta, they might say, where do you get a theta from? My reference sheet. Yeah, that's where it is. All right, you ready to move on to 35?
Yeah.
Okay, so everything we've doing has been leading up to problems like 35. Okay. And these are what are called verify, or some people even call them proofs. I don't really think they're proofs. You want to make the left side look like the right, or the right look like the left. And you have an early decision to make. Your decision is which side is more complicated. And unfortunately, the more complicated side is the side you're going to work on. So would you agree that the left side is more complicated than the right?
Yes, definitely.
So unfortunately, you got to work on that side. So the first strategy, just like we've been talking about over and over again, is to convert everything to sine and cosine. Can you tell me what cotangent is in terms of sine and cosine?
Cosine over sine.
So that's the top part. How about the bottom part?
1 over sine theta.
Good. Okay. Now here's the thing though. It's not like an equation where you can move things around. You have to, you're only going to work on the left side and hope to make it look like the right. So what can you do here? What's the next reasonable thing to do here?
Can the sines cancel?
They do cancel, and if it's not clear why, it's because when you multiply the top and bottom by the reciprocal, they obviously cancel there and cancel there. So yes, you're left with just cosine theta. And that's when you know you're done. Again, the left has to equal the right, or the right has to equal the left, depending on the problem. You ready to look at 38?
Yeah.
All right, so 38, tangent squared, I think that's a gamma, plus 1 over secant gamma equals secant gamma. I think again, it's pretty clear that the left side is more complicated. It's just got more stuff going on. All right, now whenever you see a squared plus 1, you're supposed to think immediately that that's a Pythagorean identity. So can you tell me what the numerator reduces to?
Secant squared.
Yeah, secant
Y.
squared, y gamma, whatever. Secant y. Again, you're not doing anything with the right. You're not bringing it down. You're not subtracting, dividing. You're doing nothing. So on the left, you get the two secants up top, secant times secant, and then on the bottom just one secant. So there's a cancellation there. That one cancels with that square, and it leaves you with secant y like that. So when you know what to do, which, that's really not fair, but if you know what to do, they're not that hard because you always are sort of going in the right direction. But if you don't know where to go, if you make some steps, you got to know when to turn around or when to sort of like, check your work, things like that. So 41 here, excuse me. 41 here, we got bunch of things going on the left side here. It's sine squared alpha plus cosine squared alpha. That should really stand out to you. Like if your teacher wanted you to know anything, it's sine squared plus cosine squared equals 1. All right, so those two become 1, and then you bring the rest down. This plus tangent squared alpha. Oh, and I guess some teachers really want you to cite the identity. They want you to say like, oh, sine squared alpha plus cosine squared alpha equals 1. I mean, I think it's because you're doing the because you're using the identity, I think it's clear, but sometimes they want you to write that. Now how about this? How about this 1 plus 1 plus tangent squared alpha?
That becomes secant squared,
Exactly.
right?
Yeah, secant squared alpha. And that's, I think, what the right-hand side.
Um, what is that equal 1?
Well, no. 1 plus c tangent squared alpha is secant squared alpha. And I think that's what they want you to, that's what I think the right-hand side is. I couldn't see it, but I think that's what it is.
Oh, wait. Yeah, that's what it is.
Yeah.
So the instructions say verify each of the following trigonometric identities. So by
Yes.
verify, it just means it make sure both of the sides are equal.
Yes. Turn like the left side into the right, or turn the right into the left, depending on the problem.
Okay.
All right, so we do have some time to go back to 21 and 23, or you can send over some new problems, or I can find some in one of my many books, or online stuff. What would be best for you?
Can we do 21 and 23?
Sure.
I feel like that's kind of the hardest ones.
Sure. All right. So 21. 21. We're going to make that u substitution again. So the u is almost always the middle term, cosine squared x. This time it's a squared. It really is that middle thing. And then you square both sides. When you square a square on the right, it becomes the power of 4. And the second square should match up with what's here on the left. So it becomes u squared plus 2u plus 1. And then from here, you're supposed to recognize the form of this one. This one is a perfect square trinomial. But if you did not recognize that, you should recognize that you're trying to find two numbers that multiply to 1 but add up to 2. The only possibilities are 1 and 1. So now you back substitute. Okay, so you've got cosine squared x plus 1, cosine squared x plus 1.
Okay.
So that's it. Like, and it may look like, well, maybe these simplify. Maybe there's something that you can do here. There is not. Cosine squared is plus 1 is nothing. It's not an identity.
Mm-hmm.
Right. Let's look at 23 now. 23. All right. So this is the aforementioned difference of cubes. So there's two formulas you might need to know. Difference of cubes, which is a minus b, a squared plus ab plus b squared. And then the other one is a cubed plus b cubed. This equals a plus b, a squared minus ab plus b squared. So if you stare at these formulas long enough, you realize that the difference in the beginning is this minus plus. That's propagated here, so it's the same pattern. And then these are the same, except for this sign here, which switches. So if you're wondering like, well, how did math, you know that, it's because I remembered what I just told you. Like I don't walk around remembering this, but I remember that these are the same and these switch. So in your problem, A is sine X and B is cosine X. Do you see that?
Mm-hmm.
Follow that? So you're just patterning it. You're literally patterning it there. Now, before we go any further though, I want to make one more point here, is that this part is never factorable. Never, 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 never. So once you know the formula, once you apply it, you're good. So here we go. Let's work it out here. It becomes sine X minus cosine X. That's the first part. That's the A minus B. Then it's squaring the sine squared X plus, I call it a merging because you take the A and B and you put them together, you're multiplying them, but you're really merging them, sine X times cosine X plus B is cosine squared X, like that. We're almost done, almost there. Whenever you see a sine squared plus a cosine squared, if you take more math, this will come up over and over again. These always make one, so it becomes 1 plus sine X cosine X sine X minus cosine X. And you do not multiply. You don't say, oh, let me combine these back together, because then you're going backwards. Then you're going back where you started.
Okay.
All right. It would really help me if we could stop here. I'm